Hi, so we will be looking at question remove duplicates from sorted list. Last time I messed up a little in the live session, so I'm explaining it once again. So this question is basically you have to delete all the duplicates from the list such that every element appears once. Now I will be solving this question in a recursive fashion and I'll explain the approach. Let's have this linked list as an example. So if we come across this, we have a 5 over here and a 5 over here. So these two are duplicates, so we need to remove one of them. But since we are going to do it recursively, so we need to observe some properties of the linked list so that we can solve it. So let's say your head is pointing over here and this is one of the recursive calls. So at this point of time, there's no way that you can know that this 5 or this node is a duplicate node because the link is pointing to the next node and there's no way you can go back unless once you're at this position. The only way you can go back is when the recursive call comes to a backward previous recursive call. So when the recursive call comes to the previous recursive call right here, then we can actually access both the elements and we can make decisions whether to include or which node to remove from the linked list. Now let's say at this recursive call, the head that is pointing to this node is h1, and we can actually look at both the nodes because the next pointer is pointing to the next node, or let's say the head pointer is h only. It doesn't matter actually. So since we can access the next node as well, we can also observe here that the current value is equal to the value present in the next node. At that point of time, we'll know that there is a duplicate and we need to remove one. That is, if head dot value, that is 5, this 5, is equal to head dot next dot value. So when these two are equal, we need to remove one of the values. So so instead of removing this, the value that the head is pointing to, the node that the head is pointing to, we'll remove the next node. Why? Because it makes the code a little cleaner and easier to understand. That's it. We can do any one. So let's say if you choose to remove this node, so for doing that, you have to alter the head node and then you know return the head node and then link it to the previous next node and do that. So that's a little difficult to understand. So I'm going to remove the other node. And to do that, we just have to change the next pointer. And we do that by head dot next must be equal to head dot next dot next. So this way, there is no connection from this node to this node. Hence, the whole linking in the entire linked list, this node is virtually removed. So basically, we are doing this statement. So head dot next means this pointer. We are changing this pointer. We are changing to head dot next. That is this pointer dot next. That means this. That is finally getting this pointer this way. So we are changing this pointer to this pointer's value to this node's address. In short, we're just changing links of the pointer so that the duplicate node gets removed from the list. But what if the value that the node we are currently at the next value is not a duplicate value, right? So the current value is not equal to the next value, that is 4 is not equal to 5. Then we want to keep that value in the linked list. Then we want to keep the node in the linked list. Hence, for such case, we won't be executing any statement, and we just would simply return to our previous recursive call and continue doing that. So the only time where we need to execute or we need to remove it when we find that the current value is equal to the next value. So keeping this in mind, we only have to handle this case, and it's okay if you don't write this portion in the code because this is automatically handled. So let's say, for example, you are given this linked list and you want to do it, and you want to remove the duplicate values in a recursive function using a recursive function. So for that, you will be first calling the list having the head pointer pointing to this node, right? And the next recursive call will be having the head pointer pointing to this node. Then the next function will have head pointing to this node, then this node, then this node, and finally at this node. I mean, finally at null. And at this point of time, what you want to do is you want to return. Okay, and then return. At this point, you find that there's a duplicate. You will remove it accordingly, like we discussed. Then you come back. Then you come back, and also over here you will remove it, and finally you will return the head pointer. That will be the answer. So the main concern is whenever you reach the null pointer, you will be returning back. So that would be a base case of. So the base case would be if head equal, sorry, if head dot, oh no, if head equals null, then simply return. Or instead, let's return from this node itself. That means if head dot next is equal to null, we'll be returning because there's no point going till there. So in our code, we'll be doing head dot next, or if head dot next is equal to null, then return head. But there's another edge, edge case we need to handle. That is, if the list is null, I mean if the head is null initially, so at that point of time, there won't be any elements in the entire list, hence we would also return at that situation. So if head equals null, then return. And yeah, or you should say or is a, sorry, or is a, any of the situation happens, you have to return the head. That's the edge case, the base case. So if we reach at the end or the entire list is empty, we will be returning the head node, head pointer. But initially the head pointer is pointing towards the first node. So we want to call it recursively so that it reaches the end node, right? So let's try doing that. Let's see. And to do that recursively, I'll be doing this right here, and I'll be calling the recursive function for the next head dot next. So head dot next is this node, and this will be uh, the the head pointer pointing to this node will be called for the recursive uh, function, and it will go on till it reaches the end, and it will finally return. So when it reaches the very last node, it will start returning from that position. But I mean, so this statement, what it does is basically returns from this node to the previous node. After that, we haven't written any return statement, so we need to write that after, let's say after this, return head. Okay, and it's obvious why we are doing it after, because if you do it beforehand, if you do this right here, you won't be able to call the recursive call. It will just be returned with the second statement. So now our function, what it does is it keeps on returning head from every node, and then finally returns the node or returns the head. But we haven't actually removed the duplicate elements, so we need to write that in the function as well. While the recursive function is getting called, we need to remove the duplicate nodes as well. So a common approach, or the the first thought which comes to our mind is to write it above the recursive call. Some people think that way. Let's try doing that. Okay, so if the head sorry head dot value is equal to head dot next, sorry, there's no dot in C++, next. So basically this condition, whenever we see that the next value is equal, what we need to do is we need to change the next link. Head dot next is equal to head dot next dot next. So whenever we are finding any duplicate value, we are altering the next link and removing the just next node, like in this picture. But this is not the correct code. Let's see how. How? So I have pasted the snippet of code over here to just simulate the recursive calls. So let's say our linked list is over here, this one, and the at the very beginning, the head pointer is pointing to the first node. So it just enters this snippet, and the first statement is all right, so it doesn't execute that. I mean, the condition doesn't meet, so it doesn't execute that. So it moves on to the next statement, that is, if the current value is equal to the next value. And yes, it is. So what it does is, let's add one more node actually. So at this point, this statement will execute because the current value is equal to the next value. Hence, the next pointer will be altered. Then what will happen? Since this statement is executed, it will move forward towards this statement. And what this statement does is it calls the recursive function, and the parameter it passes is head.next. So the head dot next, this is the case. I mean, in the next recursive call, the head pointer will be pointing to this node. That is in this recursive call. And to quickly explain it, let's remove the two nodes at the last. Now what happens? Again, this statement doesn't get executed because this is not the end of the linked list. It goes to the next uh, statement, and we can clearly see that the current value is not equal to the next value, and hence the statement doesn't get executed. So we move on to the next. statement. And after this, since this is a recursive call, hence it will again call this function. And the parameter which gets passed is head.next. So since the next node is not changed or whatever it is, head.next. Now at this point, this statement is correct, and from here onwards, this will return. So this from here, it will return and it will start executing from this position onwards. As you can see, we come at the very last statement, that is return head, which will finally, return return to the same function, and will start executing the statements after this. So it gets returned to the recursive call from where it was initially called. So now after that, the head will be returned. Okay, so let's do the return part once more. Now, when we were here, it returned the head, right? So the current head was head, that is pointing to this node. But when it returns and start executing statements in this function, the head pointer was not here, it was over here, right? So the head which will be returned from here, this statement, the last statement which will get executed, will be returned. Note that we don't have any, value or the any variable to store the head value, head pointer. So because we don't actually need it, we are just changing the links as we go. Anyway, so in this recursive call, the head pointer is pointing to this node, and after that, this head will be returned as a final answer. So seeing the final linked list, this is the head which got returned. And if we look at the whole string, we got 1, then we move towards the next node, again a 1, 5, and then null. So you can see that this this 1 is actually a duplicate which didn't got removed. And the reason for that is because of the fact that we started to remove from the very uh, beginning. So if we just go back to where we actually, handled this thing, let's go back, okay? So if we undo it, so we go back to the previous node. Okay, yeah, going on here. And before that, the head was at this position. And when we were at the very first position, and we were seeing that the next pointer is pointing to a node that is equal, at that point of time, what we did is we just simply changed the next pointer with the statement basically to next.next. And after that, we just simply called the next statement, that is head.next. What it does is it just moves the pointer towards the next node, and then calls the recursive function. So the recursive call goes over here, and from this point onwards, when you come at this statement, the two nodes which you're looking at is the current node that is 1 and the next node that is having value 5. So this so this node and this node were never actually compared. So that's an issue with this approach, because we after after linking this head dot next to the appropriate node, we didn't check that the link which is going on, I mean the linking we do, is a correct one or not, right? So the node that is it's pointing to, we are not checking that that it is a duplicate or not. And after that we're just simply moving the head pointer with the head dot next head dot next to the next node, and hence the comparison doesn't take place. So either we can do is we can actually introduce a condition statement that to keep on executing until we remove all the nodes, right? We can do that, but there's another you know easier way to do that without writing extra lines of code. But had there been a different value right here, let's say maybe 3 or 4 or any value that is different, this won't be error, because the the node that the next pointer points to is not a duplicate value node. So with this approach, what we are assuming that once we have linked or once we have removed the next node, which is if it is a duplicate node, we assume that the next to next node is not a duplicate node, and we simply link it and move forward with our approach. So that's that's the the place where this code doesn't run properly. So either we keep on executing it till we link it to the correct node, or there's another alternate way. Okay, so like I said, if I open console and if I put some values like, let's say maybe 1115, like we saw in the example, if we run the code, it gives us a wrong answer, right? Because it just fails to remove the one that is in the at the very middle. That's why we are getting the wrong output. But let's say had there been a different test case like double one, two, or three, or whatever. Let's take two as an example and try running it. Yes, it got accepted because the node that is getting linked to is a duplicate node. Hence, it didn't create any error. Okay, let's try submitting this code. Obviously, it would fail, but let's do it anyway to show you that this whole approach is wrong. Yeah, wrong answer. What 111 gives incorrect output. So, what is the correct way actually? You'll be surprised to know that just removing this section of code from here and writing it after this would actually work. So I just changed the order of these two, statement. I mean, this is, I'm considering a one statement, not right. So I just change the order and let's try submitting it right now. Yes, it got accepted. So let's see how this just changing the order uh, uh, gets accepted. Okay, so I have laid out the code snippets over here. So I was running short of space. So yeah, somehow I fitted the last recursive call right here. So we won't be needing the rest of the statements. It will be just getting returned. We'll see in a moment. So at the very beginning, let's say our list is this, and the head pointer is pointing to 1 for the first recursive call. So the function enters right here. The no head is not equal to null, also head dot next is not equal to null, hence this statement doesn't get executed, and it goes to the next statement, that is calling the recursive function, passing on the head dot next value. So it goes like here to here, and the value which is passed is head dot next. Again, the first statement doesn't get executed, and it sorry, my bad. Oh no, no, we are fine. So after this, the first statement doesn't get executed, it calls the recursive function again, and at this point of time it calls this function. So what we're doing is we are moving our head towards the end of the list, and after that we will be executing these statements, and you'll see why we are doing so and how that solves the problem which we were facing in the previous approach. So anyway, so once this function is called, the head pointer that is passed is head dot next. So this head head dot next, that means over here. Then again, the first statement doesn't get executed, it calls the recursive function once again. It's a little tricky to draw. Let's see how I can do that. Yes, somehow I made it. Anyway, the this recursive call just calls the this function again. Over here, what is passed is head dot next is passed. So head dot next. This pointer is passed, sorry, and the first statement doesn't get executed. It calls a recursive function again. So it calls it again, and over here, what is passed is head dot next. So head dot next. Again, the first statement doesn't get executed. It calls delete um, duplicates recursive function. Yeah, and before moving that, let's change the value of these three. I mean, just swapping this 3 with let's say 4. Okay, I mean, it's nothing going on in between. Let's assume instead of 3 it's 4, and why I'm doing so is just to is because there are 3. If there were 3, so 3 3 times 3, so it sometimes is confusing. So 4 value is much better. The whole approach is going on same, nothing is changing, just I'm changing the value, that's it, nothing else. Anyway, so we were at here. This duplicate function calls the recursive. It calls again, and what is passed is head dot next is passed. So head dot next, and the first statement doesn't get executed, hence the recursive call is made. So yeah, like at this point of time, the head pointer is pointing to, you know, over this node, and it calls the recursive function again, right? So this function is called again, and the head which is passed is head dot next. So head dot next. Now when we come at here, the first statement does get executed, and hence the head is returned, and hence it returns the head. You know what? Let's change the color of the head pointer as well as the, so that we can track what is the previous recursive call going backwards. So since we are returning the head, hence this statement goes back to the previous recursive call and start executing the statements after that. But the head in the previous recursive call was at this position. So the head at the previous call was at this position, and we are about to execute the rest of the statements. Okay, so basically the recursive call calls a reduplicate function. It executes whatever statements there are. It returns and finally continues executing from the remaining section. The remaining statements are getting executed. So at this point of time, what we what we are doing over here is basically checking if the current value is equal to the next value or not. So it is equal, and hence we want to change the next pointer towards whatever toward to next dot next. So what we do is head dot next is equal to head dot next dot next, which makes this node removed from the linked list. Now this explains, what we are doing is we are basically going from the we started from the very beginning, then we iterated till the last, and then after that we just started removing from the very last. Okay, so carrying on, after this statement is gets executed, we move to the head. I mean the last statement, that is return head, and over here also it starts executing where it left off. But at this position, but at this position, the head is pointing at this 4 node. So in this recursive call, the head is pointing at 4. So like you can see, the current value and the next value is getting checked. Over here, 4 is not equal to 7, hence this statement will not get executed, and we'll move towards the next statement, that is return the head. So like previously, 2 is just going to go. Okay, the arrow part is a little difficult to draw, but I'm pausing the recording and doing that anyway. So but at this recursive call, once it starts executing the remaining statement where it left off, in this call the head pointer is pointing to 4. So we can see that the current value and the next value is getting checked. Over here 4 is equal to the next value, that is 4, hence the next pointer will be altered. So head dot next, that is this pointer, will be equal to head dot next dot next. So the statement gets executed because the next value was equal, and the next pointer is now pointing to the next to next node. Okay, which makes the node at the middle not a part of a linked list, so it gets deleted, or there's no link to it, hence the returned linked list won't have this for node. So right here, what we can see that the for node, which was a duplicate, in the previous call, where when the head was pointing to this 4 and 7 were compared. And once the recursive call went back, like over here, 4 and 4 got compared. So we can see somehow that since once we, uh, you know, chose for this approach, we started removing from the very right end, not the left end. And it made a huge impact because because we are we with the recursive call going backwards, the head pointer is including the next very element, and as soon as it includes the very next element, it checks whether that element is a duplicate or not. Hence we are not missing out any node. But in the previous case, we were we were just bothered about the two adjacent nodes. So that solves the problem. Let's see how another 4 is getting removed. Okay, so after the executing this statement, the return head is called, and this return head goes okay, so then let's see, we can go. Okay, finally, where were we? Yeah, we. Okay, so it's just start executing from this point. Now the head pointer at this recursive call was over here, and at this position the current value is equal to the next value, hence this um, statement would get executed. So let's see what this is. So the very first thing is that head dot next is getting altered. That means this link is getting altered, and this is getting changed to some other point. Let's see what it is. So it is head dot next. So head dot next is basically this node. I mean the pointer pointing to this node. This is head dot next, and head dot next is basically this 7. Okay, that is this head dot next, head dot next, this node. So what you're changing is you're changing the head.next pointer value to head.next.next. So this node points to the pointer that is head.next.next. Since this link is broken, hence we are not able to reach when we traverse from the very beginning to at this node. Hence this node is deleted. So 4 is directly linked with 7. That's how these two 4 got removed. So like you can see, once we you know included another 4, we are actually including, while we go back, we are including the next element and handling with the existing list. All right, so whatever existing list we have, with that we are considering the newly added node in the recursive call, and we are handling that case accordingly. And because of that, we are not missing out any possible scenario. Okay, now let's remove these because that's unnecessary. Do this. Just a second. Almost done. Cleaning. Okay, we're done. So after that, the remaining statement will get executed. That is simply return and that is um, okay. So we come back to the previous call, and at this position the head is not pointing at here. Instead it's pointing one step, backwards. Yeah. Okay. So at this point also the current value is not equal to the next value, hence the statement won't get executed and it directly jumps to, you know okay, yeah, I mean, like, yeah, you get the point, right? Where it is getting executed and it's not. Okay, moving on. So it doesn't get executed, and okay. So I'm just saying, like, right here it's pointing from if to the return, and it's in this it's pointing from this statement. So, like, I should have drawn it a little more clearly, but it just means whatever the case is, after executing this whole statement, it's going to over here. So whether it needs to update or not, whatever happens in every recursive call, it just goes to the return here anyway. So it returns, it goes back and start executing, but in this recursive call, the head pointer is not over here. Instead, it's over here, that is right here. So at this point of time, yes, the current value is equal to the next value. Hence, we will alter the pointer. So the head dot next, that is this pointer, is getting altered, and the node it's pointing to is head dot next dot next. Head dot next dot next. Okay, so it's pointed out. After that, doing that, you know, just goes to the last return statement, and it returns, and it finally gives the answer, and that's return. Okay, so that's the head which is returned finally, and now let's look at the whole list. Before doing that, yeah, once we executed this statement, of course, since there is no link to go to this node, it got deleted. Yes, and finally we returned it, and now we are ready to traverse the output list. Okay, let's see. So we start with the head. Okay, then we move to one. Okay, we saw one, then we go to four. Wow. Then we go to seven. Okay, then which points to null, and we end. So this is how this question works, and that's how we can actually handle the four occurring three times, right? So that's why I replaced three with four, because three occurring three times might be confusing. Anyway, it's a small thing, but the thing is we handled multiple occurrence of any duplicate value. Why? Because we started from the very end, and we kept on including another element, and then we made appropriate changes. So I hope that clears it all. And this is the zoomed out view of the whole um, recursive calls. Okay, yeah, let's zoom in as well. Final. Yeah, this one. Okay, I think it's pretty clear. And yeah, this answer got accepted. I think that's it. And thank you for watching. And this was probably one of my best attempt to explain this. Earlier, the last time I explained a little complex approach, but this is much simpler and easy to visualize. And now that I have drawn the whole diagram, so it becomes much easier to understand. I'll upload it soon. Okay. Bye bye.